Hello everyone. Am I audible?
Yes, sir.
Yes, sir.
So any question related to what we discussed in the previous lecture and uh, anything about the previous assignment?
Sir, how much is the permissible time for the assignment to execute?
I have mentioned it multiple times, so I think we do not expect you to write a code which will run for more than 5 minutes for one ciphertext. Um, yeah, so if it is any time below that number, that is good enough.
So, sir, like grade scope is evaluating both the ciphertext, so we can take half of that time as the permissible time. Or
No. For one ciphertext, it is 5 minutes.
okay,
You don't need to worry about how much time it takes on Gradescope. So that is not something. You just worry about how much time it takes on your own computer. So if it takes less than 5 minutes on your own computer, it is fine.
sure, sir. Thank you, sir. Thank you.
Sir, I have a question.
Yes.
Sir, actually, my code is running in my local system, which is a Windows system, and it is running in 20 seconds. When I uploaded yesterday night, it was running for like 10-15 minutes or so, and then the output was ki one text was deciphered correctly, the other was not. So, is that a problem? That's the same text when I ran it on my laptop, it is running correctly, same code, everything.
So see, the resource on the Gradescope is shared, so it might take a different amount of time at a different time of the day when you upload the same code.
No,
So that
it's
is
not just
so yes, that is
that.
one part. So that is one part of the answer. And then the second part is that your ciphertext was not correctly deciphered into the correct plain text. I don't think that is an issue with the grade score. So your code should be the one which should be doing this conversion. So if uh, it is happening correctly, I don't think that there should be a discrepancy. If it is happening correctly on your computer, it should happen correctly on grade score.
What to do if this is not happening? Like,
I don't know. So there are so in fact when you are uploading a code on Gradescope, it is not running on just two ciphertext. It is running on six ciphertext. So two plus four additional. So it might take more time than what you are probably expecting. Uh, so that is one other thing that I wanted to tell again. So I all of these has been clarified on chats, but yeah. So your code is running on six ciphertext when you upload a code on Gradescope.
I was more worried about the accuracy, sir. Actually, same ciphertext. I am. Matlab, it's running. I mean, in fact, I checked the third one also. That example that was given in the folder. All the were deciphered within few seconds, and it was coming correct. But I mean, great scope. Okay.
So same thing happened with me, but after changing some rearrangement, after doing some rearrangement in my code, then it will work properly on Gradescope.
Okay, good.
Rearrangement like.
And like where I print actually before I am printing like plain text and key outside the function, and after when I print this inside the function, then it will work correctly for both the ciphertext. But if I print outside the function decipher function, then it will give correct answer for only one code, ciphertext 2 maybe. Yeah.
You mean I need to disable all the print statements?
Oh
Yeah.
yes, yes. So yeah, I also want to mention that you should not print anything, any debug statements. So it was very clear in the instructions that there are only three things that you should be printing on the terminal: the ciphertext, the plain text, and the key. So all debug statements. So none of the debug statements should be printed, and the output should be just um, there should be just two outputs, one plain text and one key, the deciphered key. So you should not give any other output. So yeah, so if you
Right,
just
sir.
be
Now
careful with those two things.
right, sir. I got my mistake. I'll correct it, sir. Thank you so much.
Okay, good. So one more quick thing. So the assignment 2 will be out on Monday, and it will again be coding intensive assignment. Um, but I think you should be able to manage, and the deadline will again be 1 week. So hopefully, we will be able to successfully complete it. And then there will be a long, not long, but again a break of 1 or 2 weeks, and then you will have the deadline for mid-semester report, project report. So I would suggest that you start working on that project, course project now, so that you at least have the title or the idea established and your partner established, so that you can probably come up with a nice midterm report by the deadline. So I have already announced the dates, the deadlines, tentative deadlines. So hopefully we will stick with those. We will see how things evolve. So any question related to the deadlines for the project? Okay, so before the minor, you will have only 2 assignments, and then after the minor, you will have 2 more assignments, and then this project will continue throughout the semester. Okay, so let's move to the topic today. Yes, one more thing. So in the last lecture, I had left one question open as to what are the conditions in which AES CBC mode, if utilized for authentication as well as encryption, might lead to some issues. In what configuration? So has someone tried to figure that out? No? Okay. Okay, then we will probably discuss that sometime later. Okay, so let's move to the agenda today, symmetric key distribution. Okay, so until now, what you have understood is the different, you can say, protocol primitives which could be utilized to secure systems. So this just means that now you understand that if you have a symmetric key, then how will you utilize the symmetric key to achieve confidentiality and integrity of the messages that you would like to communicate. Then similarly, if you have asymmetric keys, how will you utilize those asymmetric keys? So now we will move on to some more network related question that, or you can say that if we would like to put these ideas in real world, then what are the challenges that we will have to face, and then how will we solve those challenges? Okay. So I guess in the next 10 lectures or 15 lectures, in the next or before the minor, all lectures will be following this thread that okay, now that we know that if you have a secret key, you can do encryption and authentication, but what will happen in a real world environment, and we will see how those different challenges are solved. So the first challenge that we need to solve is that how does the sender and the receiver obtain a key? Okay, so we had just said that there will be a trusted third party, and then the trusted third party will send a secret key to the sender, and then it will, if it is symmetric key, it will send the same secret key to the receiver, and then the sender and receiver will start communicating securely. But there might be different challenges in actually doing so. So we will talk about those challenges, and then we will see what design choices are made in order to solve those challenges. Okay, so basically slightly different terminology. So the trusted third party that we have been talking about is now being called key distribution center. Okay, so that is the basically role of that trusted third party to distribute the key. So therefore we are referring it as key distribution center, KDC. Okay, so then what is it that will happen in a real world system? This KTC will share a secret key with the sender, and then the same KTC will share a secret key with the receiver as well. Okay, so these could be called master key. So that master key is now shared between the sender and the KTC, and then there is a master key which is shared between the receiver and the KTC. Okay, so so here what I'm referring to is one of the concepts that we discussed in the class as well, that you may have a KDC and we may have a sender and we have a receiver. So we know that if the sender has a secret key K and the receiver has a secret key K, then how to secure the channel. Okay, so then if we know that, then if the sender and the KDC also has some, let me just call this the key between sender and receiver as probably SR. Okay, so if that K underscore SR is the key between sender and receiver, and I know what to do, how to make the channel secure using this KSR, then if I have this KSK, which is the master key shared between the sender and the KDC, and if I have one other shared key between the receiver and the KDC, then I also know how to securely communicate something over this channel. Okay, so that is the premise on which we are proceeding. Okay, so therefore we are saying that there are master keys, so pre-shared secret keys between sender and KDC, and pre-shared secret keys between receiver and KDC. And then we have a session key, which is the KSR in this figure, the secret key that needs to be utilized between the sender and the receiver. And then the goal here is to come up with a protocol, key distribution protocol, which will enable sharing of KSR, the session key, using the master keys, KSK and KI. Okay. So this is the setup. Okay, so now what can we do? So there could be some ways in which this could be done, but not all different ways will be secure against variety of attacks. Okay, so first we will see what could be the basic thing from the knowledge that we already have from the discussion that we have done in this course. What can we do in order to do this distribution of keys? Okay, so what the sender could do is, the sender could transmit a connection request packet to the KDC, which means that the sender would indicate to the KDC that it would like to initiate a connection. And then, but the important point to note here is that this connection request packet will be encrypted using the master keys that is shared between the sender and the KDC. So it will utilize that key to encrypt that communication. Okay, or encrypt as well as authenticate that communication. Okay, so then the KDC, what it does is it generates a unique one-time session key. So remember, this session key will be utilized by the sender and the receiver. So it generates a session key, encrypts the session key using the master key shared with the sender, and delivers the encrypted session key to the sender. Okay, so now the sender has the session key that it can utilize. Again, the KDC will encrypt the session key with the master key shared with the receiver, and then the receiver will also have the session key. Okay, so both now sender and receiver have the session key. And now the sender and receiver could start communicating using the session key. Okay, so this is quite straightforward what could have been done. Any question related to what is being done here? So this is the basic distribution mechanism that could have been done using the knowledge that we already have in this course. And I will tell you what actually happens in a real world system later. But any question related to what we just discussed?
Sir, I have a question.
Yes.
So, sir, the master key, so the master's keys are shared to all the senders by KDC?
Yes. So each sender, so if there are, let's say, 5 senders in your network, then the KDC will have one key, one master key shared with each sender, which means there will be 5 master keys, and each sender will have one master key that it shares with the KDC. So the number of senders, yeah.
Uh, sir, in a case when there are multiple senders, for example, like in real world scenario when there are millions and near to billions devices, so all these are having different keys, master keys with
They
particular
could
their
have for this
KDCs.
setup, yes. So therefore, this is not the setup in which things work in the real world systems. So when you think about the symmetric key based networks and the asymmetric key based networks, so both have their challenges, and you have correctly identified one of the important challenges when you depend only on the symmetric key based system. So if you think that in a world where we only depend on a symmetric key based system, then there will be a trusted third party or KDC, which will have to share this symmetric key to each sender and to each receiver. So that will be definitely something not a good design, and because the KDC will be a bottleneck.
Thank you, sir.
Sir,
Ritika, yeah, are there some common third party? What do you mean by that common third party? So, trusted third party by its name means that a sender and a receiver who would like to communicate, they trust into one of the entities, which is called the third party, because the sender and receiver are the first and the second parties. So, whoever they trust, they become the trusted third party. It is not that there could be only one trusted third party in the whole network. There could be many trusted third parties. It is just one of the ways of saying that there is some entity in which both the first and second party trust. So the sender and the receiver trust. Yeah, go ahead.
Sir, in this mechanism, since like sender initiates the
Vijay, I lost your voice.
audible now.
You are audible, but I'm not able to hear you clearly. Yeah, please go ahead again.
In this sender,
No, probably test your connection. I am not able to hear you clearly. Or type your question in the chat. Okay. Any other question related to this basic distribution mechanism?
Sir, how is KDC ensuring that the security and safety of the master key which it is sharing with the sender, because that also can be done away with the man in a middle attack, something like that.
Yeah. So the same threat model that you think will be applicable to the channel between the sender and the receiver, that same threat model could also be utilized for the channel between the sender and the KDC. But what we are doing is we are saying that if we solve this problem between sender and receiver, we will be able to solve the problem between sender and the KDC by considering another layer of KDC. So there will be another, so we talked about it probably 2 times before, that it is a layered way of thinking about security, or chained way of thinking about security. So if we solve this basic problem between one sender and one receiver, assuming that there is a trusted third party, then we could solve the communication between the sender and the third party by considering a fourth party in which both the sender and the third party will trust. So this is the way you think about solving the problem. And at some point there will be a root in which everyone will trust. So that will be the root of that chain. But yeah, the same threat model applies to uh, any communication channel. Okay. So currently we are focusing between the securing the securely delivering the key to the sender and the receiver, making some assumption that there will be some master keys that will be shared with the trusted third party. Okay. So now we will talk about a real world key distribution protocol, a secret key, symmetric key distribution protocol, which is very popular. And you will see that it is much more complex than the basic distribution mechanism that we have come up with. Okay. Okay. So let's look into some of the components here. So we have a client. Okay, so think of a client as the center that we have been talking about, and it is being represented by C. Then we have the server. You can think of server as the receiver that we have been talking about, and it is being represented as B. And we have an authentication server, so AS, and then we have a ticket granting server, TGS. Okay, so the trusted third party's role or the KDC role has been divided into two parts. So one is the authentication server. So it had to authenticate the senders and receiver, or the client and the server, and it also needs to give out the keys, and therefore the other function that the trusted third party was doing was sharing keys. So now those two functions of the trusted third party are now divided into two parts. The authentication, and you can consider that these two parts could be implemented on just one entity, which we have been calling trusted third party or KDC, or these two parties could also be two different parties. So that will actually enable your network to have more trust into the infrastructure. So, so there will be one party which will be called the authentication server, and the second party will be called the ticket granting server. Okay, so with these four entities, now we will see what happens. Okay, so we have these three boxes here. Okay, so the first box is the first two steps. You see that the communication is happening between the client and the authentication server. The second box is the communication between the client and the ticket granting server. And the third communication is now happening between the client and the server. Okay, so the receiver or the sender or the receiver communication. Okay, so these are the three boxes being shown here. Okay, so now let's see what are some of the things that are being communicated. Okay, so the first message. So we have some payload going from client to the authentication server. So remember we said in the previous slide that the client will indicate that it would like to establish one new connection. Okay, and that is what is happening in this first method, that some information is being shared with the authentication server to indicate the start of a new connection. Okay, so there will be some options that will be uh, uh, shared between the client and the authentication server, so that the authentication server could actually take some steps. So these options could have different flags, and yeah, so this is just one optional set of bits that could be sent to the authentication server, and then it will the message will have the client's ID as well. Okay, so you could think that probably because this communication between client and authentication server will already utilize the master key shared between those two. Probably adding the identity may not be very useful, but there are some attacks which are possible if you do not include the identity of the sender and the receiver in the payload messages. Okay, okay. So this is just the IDC is the identity of the client. Then realm of clients. So this authentication server might be serving a large number of clients, and it might be defining many subsets of clients in order to manage the network or manage its load. And therefore, the client may be provided a certain realm in which it is operating. So it is just, you can think of a subset of the users in that network. The client will indicate what subset it belongs to. And then this ID of ticket granting server. So this message will also have this information that what is the identity of the ticket granting server to which this client should be directed to, or it wants directed to, and then times. So, um, so so you think of the previous scenario we talked about that if you have a master key, you could get an encrypted version of the session key from the authentication server. But think about a scenario where you will be requesting a connection, and then the attacker captures your packet and then uh, replace that packet back to the authentication server. So then, or any packet that you are utilizing to communicate between the sender and any receiver, how about the attacker captures that packet and then replays it? So in order to prevent this type of replay attack, the established mechanism is to utilize a counter, or also utilize an absolute time, so a time at which a message is being generated. Okay, so so this is something that you will see in all packets, the time. Now in this case, this client, by including some information or requesting some information about time, it is indicating multiple things. So at what time um, the request was generated, at what time the request will expire, so these kind of things. And then you always have a nonce in a packet, typical communication packet. And the reason why you need a nonce is because this again this so one part was that replay attack has to be prevented, but when you would like to also have messages which will be communicated between the two parties, and these two parties are going to remain the same. So even if you add everything same, so everything will have some structure. So time will have some structure, the options or the realm, the IDs, all of them will have some structure. But when you would like to do authentication on encryption, you would like to have some randomization in the message, so that it is much harder to replay that information or to recreate that information. And therefore, you would see the nonce, which is just a pseudo-random number or pseudo-random sequence of bits, which is changed in every message. So that is the typical role of nonce. So nonce is basically a pseudo-random sequence of bits. Okay. So I hope the role of all these different components of the payload of this first message is clear. Any question related to the use of time or use of nonce in this packet? Okay. Okay. So now we will move to the message 2. Okay. So in this message 2, the authentication server is replying back to the client. Okay. And then you should expect some of the things from first message, what could be the components in the second message. Okay. Okay. So the first thing to note here is that the things that were talked about earlier. So the realm will be part of the next message. The identity of the client will be there, and then there will be a ticket. So I will talk about the ticket first. So what is the ticket? So ticket is basically the encrypted version of the following components, and this encryption happens using the key that is being shared between the client and the ticket granting station. Okay, so the client. So now that you have these four entities, you could think of the keys that will be shared between them. So the client will have two shared keys, or you can think of two master keys. One master key shared with the authentication server, one master key shared with the ticket granting server. So this TGS is the secret key, which is actually shared only by between the client and the ticket granting server. Okay, so now so you will have some information related to the connection, and so this ticket basically is actually sharing some information that will be important for communication between the client and the ticket granting server. Okay, so that is what this ticket means, that what you are, so the authentication server is giving a ticket to the client so that it could communicate with the ticket granting server. Okay, and then it is also encrypting it using this KTGS. Okay, so because this has to be a confidential information to the client. Okay, and then you also have these different encryption of this a key which is going to be used between the client and the ticket granting server, the one particular session key. Then again times related to at what time the message will expire, or what will be the duration of the validity of that message. Then again the same nonce. So this time it should have the same nonce. And then realm of the ticket granting server. So there could be many ticket granting servers as well. So you also define what is the realm of that ticket granting server, and then ID of the ticket granting server. So this all of this will be communicated to the client. So you see that the authentication server will not just send an acknowledgement that go ahead and talk to the ticket granting server. You are authenticated, you go ahead and talk to the ticket granting server. So in order to make sure that this authentication proceeds in a correct way, permission that is now given by the authentication server to the client to communicate with the ticket granting server, it includes a lot of information, not just some encrypted key that it could utilize with the ticket granting server. All of that information, so each individual information again is very important to include, and I will encourage you to read the book to see why using one of them could lead to attacks. So in the book, they have very nicely explained Kerberos in a stepwise first manner. So they started with some, so in the book, the authors have started with one version of Kerberos, and then they showed that this might not be a good way, so we should include something else, and then they again say that this might not be a good way, so then they include some other uh, components as well. So what I'm showing here is the final version of the Kerberos. Okay. So yeah, so this second message is basically a ticket that is being given by the authentication server to the client, so that it could start communicating with the, so that the client could start communicating with the ticket granting server. So is that part clear? Okay, so if there are some parts not clear, think about them, and then I will clarify probably uh, at the end of the whole discussion about Kerberos. Okay, so now the client can go ahead and talk to the ticket granting server. So again, there will be some options that the client may want to have. Then now it is sharing the identity of the server to which it will talk, or identity of the receiver to which the client wants to talk. And then now you see that there is another nonce that is being utilized to communicate with the ticket granting server. And then the ticket TGS, which was received from the authentication server. Okay, so this ticket is the one which will be validated by the ticket granting server to make sure that this client has actually gone through the authentication server before coming to you. And then this authenticator C, you can think of it just a message authentication code in order to validate whatever information is being added here as part of the payload. Okay, so that this third is also very straightforward, third message that is going from client to ticket granting server. Now the fourth message, the message that is going from the ticket granting server to the client, that is more interesting. Okay, so you see that so this message has, of course, the realm of C and ID. So those two things have to be part of the payload. And then it has this ticket underscore V. So now this ticket granting server is giving the client a ticket which it could utilize to communicate with the receiver or the server. So remember, V is being indicated as the server. So now the client is being given a ticket so that you would now communicate with the server. And then what you need to make sure that it also receives a key that it could utilize, and that key will be encrypted using the master key that will be shared between the client and the ticket granting server. So you see this K, C, comma V. So this is the key that the client could utilize to communicate with the server, and this is encrypted using the master key. Then you have times nonce to realm of V and ID of V as well. So all of that as part of that encrypted text. Okay, so one thing that I would like to again go through is that this ticket. Yes. Was someone speaking about something? Okay, so then so yes, so this ticket V, you notice that there is this all this information is being encrypted by a key KV, which is the KV is the master key that this server is sharing with the authentication server. So, or this trusted third party. So that key is being utilized by this TGS to actually encrypt this whole thing. So this ticket V, remember this ticket V, it is possible that this ticket V does not make sense to the client. So client may not be able to decrypt this ticket V, but it could utilize this ticket V. And if it utilizes with the correct server, correct V, then this ticket will be valid. Okay, so that is one point that I wanted to highlight, that the client may not be able to decrypt this ticket underscore. Okay, and then finally this authenticator C is basically you can think of it as message authentication code. Okay, so any question related to this block B, the messages 3 and 4? So now let's look into this last block, which is now the communication between client and the server. Okay, so now this client will send this ticket V, uh, which will have the encrypted session key, and it will also authenticate this key by using this authenticator. Okay, so now when this server receives that ticket and it is able to decrypt that ticket, so now it will know what is the value of the session key that it has to use. Okay, so after decrypting this ticket key, it will be able to find out that session key. And then what it will do is, it will take the session key and then it will try to do some more things with it. So for instance, first do a handshake. So rather than starting the communication right away, it will want to do some handshake and share some parameters. So for instance, it may say that let's not use this session key for next messages. So we will use this session key to generate more keys, and then we will utilize those keys to start communication. So it can generate a sub key and then start that request to let's use that key. It could also send some sequence number. It could be just a counter to make sure that it is using this the same sub key, or this that sequence number could be related to anything. Okay, so these are some of the things. So this TS2 that you see here, that is also one time parameter. You could say that when the server starts communicating with the client, it will record that time and it will share that time with the client, and this information could be further shared to the ticket granting server or the authentication server for further processing. But basically this is just again a timestamp. Okay, so this is the end of the key distribution part. So now you had this trusted third parties role divided into two parts: authentication server and ticket granting server. Authentication server validated the client, gave it a ticket so that it would communicate with the ticket granting server. Then client went to the ticket granting server, took another ticket from the ticket granting server to now communicate with the actual server, the receiver. And then it went and gave that ticket to the receiver, and receiver validated that ticket. Now the receiver knows the secret key that it should utilize to communicate with the sender or the client here. That is the basic story, but there are the different parameters, the different um, components that you see here of the payload in each of these messages. Each of them are very important, and you should understand their role in more detail by reading the book. Any quick question related to these different parameters? Question? Okay. Okay, so then let me quickly ask a few questions to see if you understand that or not. Okay, so um, should I have a clean version? Probably I can. Or we can go with this. Okay, so let's start with the probably second message here. So you see that this ticket TGS. So this uh, ticket TGS is something which is encrypted using this key K underscore TGS, and it carries the key A underscore C comma TGS. Okay, so that is basically um, the secret key that this client could utilize with to communicate with the ticket granting server. Okay, so now can someone tell me if this client would be able to decrypt this ticket underscore TGS or not? Am I audible? Can someone reply to that? Am I audible or not?
Yes, sir, you're audible.
Okay. Okay. So I think I did not do a good job of explaining this, Kerberos, but um, yeah. So can someone just try to answer this question based on whatever you understood from this discussion, whether this ticket underscore TGS, which is utilized in the message 2, can the client decrypt this message? So, okay, so let me just repeat first explain it and then probably repeat the question. So this KTGS is a secret key which is shared between the authentication server and the ticket granting server. Okay, so that is the KTGS. So wherever there is just one subscript and there are no two subscripts, you can say think that the other subscript will be the authentication server. Okay, so when you see just K underscore C or subscript C, that means by default it is K subscript C comma authentication server. So that is the key that is being shared with the authentication server. So that is how the notation is here. So now when you have this K subscript TGS, this means this is the secret key shared between the ticket granting server and the authentication server. Okay. So now with that information, can somebody tell me if the client will be able to decrypt the ticket subscript TGS or not in the message 2?
They won't be able to decrypt it because they don't have that key that is shared between authentication server and the ticket granting server. So that ticket is only meant for them to pass to the ticket authentication server and not to basically decrypt it.
Yes. Okay, yeah. So that is correct. Anyone would like to add something to that? So basically, this authentication server is giving it. You can think of it as a locked box to the client, which the client cannot unlock. Okay, so that could be an analogy, but it could always give that locked box to the ticket granting server, and the ticket granting server could unlock it and then verify whether to obtain the key that it could utilize to communicate with the client. Okay, so the ticket and subscript TGS cannot be decrypted by the client. Okay, so that is one part. Then the second part that I would like to again ask, so I already talked about it. So how does adding a timestamp stop replay attacks? So can somebody tell me and probably explain it better than the way I explained? So how does adding a timestamp stop a replay attack?
Sir, like for example, Alice is sending a message to Bob, ABC. Okay. So if there is a man in the middle, and then that man in the middle can intercept that ABC and can send it at later point in time. Okay. Whereas if I add a timestamp, this will not be possible, sir.
Mhm. Yeah.
Sir, it would be
So,
something like an OTP which we send. No, it is only valid for some time. So later on, if you try to do any transaction using the same OTP, your server will not recognize it. It will consider it a false something. So basically, time stamping also doing a somewhat similar job.
yes. So I guess that is uh, yeah, that is correct. So it is very similar to that. So you get an OTP, which you think of a nonce. So OTP here you could relate to the nonce that is being shown on this in this Kerberos protocol, and then you also have a timestamp. So in this case, in the case of OTPs, you have this 10-minute window in which that OTP will be valid. So very similar concept here. So that nonce will be valid only within a certain window, and therefore you could utilize that nonce to do whatever it is. So in this case, validation of the ticket only within a certain time window. So that is how adding timestamp stops the replay attack. Okay, good. Any question that you did not understand on this slide? Any uh, parameter that you think requires more clarification? So I would say that please go back and read about it in the book. The book does a very good job of building this Kerberos in steps. Probably I should have also done that, but I thought to just describe Kerberos, the final version of the Kerberos. Okay, good. If we don't have a question, so then we will move to the part of public key distribution. So this is it about the secret key distribution or symmetric key distribution. Now we will talk about the public key distribution. Um, and on Monday, and then on Monday you will also have your assignment. So that's it. So the session in the evening today I think I was hoping that I could discuss some project related issues that you might be facing. So if other than that, I don't think there is, I don't see much of the need for discussion in that session. But if you have any question related to the assignment or related to the project, please feel free to join that session. Okay. And yeah, that's it for today. Any last comment?
Sir, in Kerberos, do the middle party have the access of the communication confidentiality? It can break.
Okay, so yeah, so see the threat model here is that the attacker has access to the channel and it is trying to break the confidentiality and authenticity of any message that is being communicated on any of the channels. Okay, so the channel could be between client and server, the channel could be between client and authentication server, or the client and ticket granting server. So that is the threat model. So it is true that it is trying to break the confidentiality and integrity of the messages, but it cannot, and that is the reason why it cannot is because there are some encryption and authentication mechanisms being utilized here, and we discussed how encryption and authentication prevents those different types of attacks. So the attacker is trying, but it cannot. So you, yeah.
So generally, both of these segments, authentication server and ticket granting, they are from the same entity. So like we cannot say them that they are middle entity.
No, so they could be, but they could be different entities as well. So they could be, so it is the, so initially you could have both functions running on the same entity, same device, but you could also have two different devices running these two services. So both options are possible in this Kerberos, in this design of Kerberos. Okay, so we will talk about some more things in the evening and then we will meet again on Monday. Okay, bye bye.
Thank you, sir.